Alright, so here's a problem. Again, we want to construct the shear force and bending moment diagram for this. We have a nice continuous load. Just a little aside, if I had to write an equation for shear force and bending moment as a function of x, could I do that here easily? I think so. So a strategy would be to do that and simply just plot the equations. But that's not the kind of the graphical nature of shear force and bending moment, and I want to do that today. So let's start like we always do. Let's look at the reactions. So on the left-hand side, I'm going to write positive shear at A, and on the right-hand side, I'm going to assume positive shear at B. Remember, these are shear forces, not reaction forces. So I'm going to sum moments at either A or B to find those reactions. And so to do that, it's going to be easier to handle the concentrated force that's equivalent to this distribution. So what's the area under this triangular curve? It's 1/2 base times height, right? So that's going to be 1/2 18 times 4. What is that, 36? So we're going to have an equivalent force of 36 kips. I'm going to decide to sum moments about A, no particular reason. But when I do that, I'll want to know the distance from A to that force. And what will that distance be? Yeah, it'll be 2/3 of the base, and 2/3 of 18 is 12. So I have all the pieces I need. So let's come over here and sum moments about A. Make sure it's in equilibrium. So when I sum moments about A, this concentrated equivalent force is going to create what kind of moment about A? Positive or negative? Negative. So it'll be minus 36 kips. The moment arm is 12 feet. And then the way I've assumed my positive shear at B, it also creates negative moment and has a moment arm of 18. So it looks like the shear at B is going to be negative, and it's going to be 24. Does that sound right? And then we can sum forces in the y direction. Make sure the free body's in equilibrium, and from that we should be able to find the shear at A. So my shear at A is acting up, minus the shear at B, which is down, minus the equivalent force, which is 36 kips. So when you solve for the shear at A, you get 12 kips. Don't forget, because the shear at B is negative, when you plug it in here, minus a negative will be positive. Okay? So we have our reactions. So now let's come over here and kind of draw a template for our left and right edges. And you'll notice, since the load is continuous, there's not really any points that seem like I know what's happening. So I'm not sure if I have any other points of interest in the graph just yet. So I'm going to go ahead and establish a positive x-axis and a positive shear, and tell you all my shear values are going to have the units of kips. So starting at the left side, because we always work left to right, positive x direction, what's our starting shear value? It should be the shear at A, which is 12. And where else do I know the shear? I know the shear at B, and what's the shear at B? Negative 24. So I kind of know where I'm starting and where I should end. So let's look at our two relationships. I know the change in shear is going to be the area under the load diagram. And we also know that the slope of the shear diagram is equal to the load. So using the first one, the change in shear is the area in the load diagram. So that means the change in shear from A to B should be the area under the load diagram from A to B. And what's the area under the load diagram? Now, we've already figured it out with the concentrated equivalent force in this case. So that's 36. And is that positive or negative load? It's negative. So we're going to say 12 minus 36, and we get minus 24. So that works. So next, what's the slope look like? Well, the slope's equal to the load. So I go up here, starting here at left side. What's the load at A? 0. So I should start off at 0 slope. And the slope gets linearly larger to a maximum value of 4. And again, is that a positive slope or a negative slope? It's negative load, so it's negative slope. So in this case, if I actually looked at that, that would be a slope of minus 4 to 1. And now I can kind of connect those spots. I didn't do a very good job of tying it in there, but you get the idea. Okay? Now we have a challenge. What's the challenge? Yeah. Now we've crossed the axis, so that now becomes a kind of point of interest. Why is that an interesting point? Because when the shear is 0, what does that usually mean about the moment? Maximum. So now, I'll go ahead and finish constructing my moment diagram. So there's my positive x. I'll say positive moment is up, and all my values will be kip feet. Now what do I know about the moment? What's the moment at A? Should be 0. And the moment at B? Also 0. Now how am I going to find this value? Let's call it x1. Well, remember, the change in shear is equal to the area in the load diagram. What's the change in shear from A to this point? Yeah, so the change in shear should be negative 12 kips, right? And if I extend that point up, you can see what the area under the load curve would be for that segment. What would be the area under the load curve? Well, what's the area of this? This is 1/2 base, which is x1, times height. What's the height here at an arbitrary distance x1?
x1 times 36.
Yeah, so
Or times 4.
what's the slope of this line? Rise over run, right? So let me see if I can write that here. So the slope of the of the load diagram is going to be 4 over 18, which I can, I guess, reduce a little bit to 2 over 9. So that means that my actual function of the load is what? 2x1 over 9. That's the height right there as a function of x1. So if I integrate that, 1/2 base times height, what do I get? If I integrate this load, you're going to get x1 squared over 9, right? You guys see that? So now I just set these. Oh, by the way, I'm sorry. This is negative too, because it's a negative load. So you set these two things equal. So you get negative 12 equals negative x1 squared over 9. So what is x1 equal to? It looks like it's going to be the square root of 108. What's the square root of 108? 10 something, right? 10.31. Now, obviously, a solution to this equation would be negative 10.81, but that doesn't make sense to us, right? It's off our thing.
I don't know if it matters, but it's 10.39.
Oh, 10.39, sorry. So now I know that when I find the value of the moment, we're going to know where it's going to occur. It's going to be 10.39 feet from the left. And you'll notice that's not the middle of the beam. The middle of the beam would be what? 9, right? So it's a little bit to the right of the beam, which makes sense. You see the load is shifted to the right. You'd expect the maximum moment to be there too. You guys with me so far? This is a little bit different. So now the second equation for moment, we use that the change in moments, the area under the shear diagram, and that the slope of the moment diagram is equal to the shear. So the change in moment, let's say the change in moment from 0 to x1 should be the area under the shear diagram. So how do I find this area? Now we do have an advantage. What kind of section does that look like to you? That's a parabolic section. See, because it starts off with a 0 slope. So actually the area of a parabolic section is 2/3 base times height. Our height is 12. Our base is 10.39 and then 2/3. So what would that number be? I'm going to need some help with that calculation. So that should be 10.39 times 12 times 2. What'd you guys get? 83.12? That sound reasonable? 83.12, that's what I got, yeah. So that means that this is a positive area, so that means I'm going to start at 0 and I'm going to end up at 83.12. What's the shape of the curve look like here? Well, it's given by the shear value, and the shear value starts off as a positive value and decreases to 0. So that means I would start off with a positive slope and decrease to 0. In fact, if you had to put a number on it, this slope would be 12 to 1. So I know that part of my curve is going to be shaped like that. Here's where things get a little tricky. The remaining section of this parabola is not a parabolic section and not a parabolic spandrel, because you'll see that at the beginning of that section or at the end, the slopes are not 0 in any direction. So you're kind of stuck in terms of a quick formula. So really at this point, there's not much you can do from a geometric point of view. Now you could continue, obviously, because since I have the load curve, I can integrate that and actually get the shear, and then I can integrate the shear diagram or the shear function and get the moment function and just plot it. So this is really all we can do at this point. You would just have to almost assume right now that the area under this part of the curve would be negative 83.21 and bring you back to 0. But I don't have any way of showing you a quick calculation. Now the reason I'm showing you this problem is it looks pretty innocent when you start, but you can see that it provides a significant challenge in the graphical approach to shear force and bending moment diagrams, because you're kind of left with, oh man, what do I do with that? Right? And I don't know how to tell you how to get rid of that. So I would just have to hope that the change in the shear area in the shear diagram would be this negative change. You would start at 0 slope and end up with a big negative slope of minus 24. And that if all was good in the world, you would get a shape that looked like that. But really, I can't verify that part with the geometric approach that we've had so far. So, like with all techniques, there are advantages and disadvantages. So I wanted to show you this one to make you aware that when you have linear loadings like this, or these triangular shaped loadings, it can get a little tricky when you try to use just geometry to find your moment diagram. You might have to actually stop, write your equation, and find the moment equation and just plot it. So a little bit different. So this is just one that we can kind of use as a discussion. So any questions about that or any comments about that one? Yes?
How did you come up with that work question right there? How did it end up being a negative x1 squared divided by 9 again? We came up with an equation for the load right here, and I put it in here and just integrated it. Now, what you could tell right now with some degree of confidence is that you know where the maximum moment is. It occurs 10.39 feet from A, and you know the value. And that's really, as a structural engineer, that's all you'd really care to know about right here. It's what the maximum moment is and where it occurs. Yes?
When you integrate that, could there also be a constant too?
Oh, there will be.
Oh, okay. Is it just 0 in this case? Or?
No. When you integrate this function, if you want to take this load function and make a shear function, okay? See, this is an in-depth. So what I'd actually do here, if you want to actually find the equation for shear, you would integrate the load function, which when we did that, we would get minus x1 squared over 9 plus an integration constant. Okay, now how do we solve for this integration constant? Right. We know that when x is equal to 0, what's the shear value? 12. So this curve has to fit the fact that when x is equal to 0, I know the shear is 12. And that's the easiest one to fit. So you can now see that our actual shear equation would be minus x1 squared over 9 plus 12. That I could integrate and generate another integration constant to find the actual equation of this line here. But once I know this function, I could simply just integrate it from 10.39 to 18, and that would give me the change, right? That would give me the change in a moment. So this would be kind of a combination problem of partially it would be the graphical approach, and then at some point we'd have to drop back and write functions. And thank goodness it's a continuous function, not a discontinuous function. They can get quite challenging. So any other questions about that?